from IIT Bombay, and she speaks on twist knot invariants and volume conjecture. Thank you. So, I am going to talk about some work which I did 5-6 years ago, and I thought this is an arena where mostly mathematicians and some physicists, I guess, will be able to appreciate what is going on from the physicist point of view. Okay. So, I work in Chern-Simons field theory. So, I will try to give a brief overview of how explicit polynomial computation can be done within the Chern-Simons field theory approach, and then I will switch to specifically the twist knots, and from the twist knot invariant how we try to look at the generalization of Kashif's conjecture, which is called as the generalized volume conjecture and quantum volume conjectures. So, I will spend some time on that. Okay. So, typically you need a 3 manifold and we will confine to a 3 sphere S3. So, this provides a very natural framework where we can put objects like knots inside the 3 sphere and study their invariance. So, typically when you ask any quantum field theory person, they will say what is the action. Okay. So, that is the way any physicist will ask. So, action is nothing but a 3 form on a 3 manifold here, okay, and these are what we call it as the gauge fields or connections, and they will be valued in some specific, you can choose a principal bundle with gauge group G, and these gauge fields or connection will be valued in that gauge group. Okay. So, it will be in the adjoint representation. So, this was the starting point where a lot of excitement happened between mathematicians and physicists. Witten came up with the proposing the Jones invariant today he was explaining, Ilya. So, you can reproduce those Jones invariant using the Chern-Simons field theory approach. So, or in other words, it gives a nice 3-dimensional definition for knots. Most of the things which you see are projection, but Chern-Simons theory gives you a projection and you can explain or reproduce the mathematician's results from a simple quantum field theory having an action which is this, and you are going to consider observables in a quantum field theory. The observables are nothing but they are knots. Okay. Okay. So, observables are nothing but knots. As a physicist we call it as a Wilson loop operator. So, it is a kind of a loop, or you can treat it like a word line in a general physics language. So, this particular knot which I have chosen for reasons which will become more clear when Abhijit starts talking about hyperbolic manifolds which are not complements, and this is the famous figure 8 knot. So, I just put it for completeness so that it will remain in your mind, and you can choose the gauge group, you can choose it to be a compact semi-simple Lie group, and these R's are various representations which you can put in the gauge group. Okay. So, need not be the defining or fundamental, it can be beyond that, need not be adjoint, it can be any other representations. So, the Wilson loop operator will have an information about what is the knot and also what is the representation of what gauge group we are choosing. Okay. And this formally has an expression in terms of the connection. Let me not get into the details, but as a physicist we would like to find expectation value, or you can call it as average values of these operators in a quantum field theory, and they will turn out to be, I have shown it in an angular bracket, do not confuse this with bracket notation, but this is what we call it as an expectation value of Wilson loops, which is nothing but will give you some result, and that we call it as a not invariant, and the result will have information about representation, will have information about the rank of the gauge group, and also have information about the knot k. Okay. If you change the knot, this result will change. If you change the representation, the result will change. If you change the gauge group, it will change. So, we have ocean of results here. Okay. So, it is not just one answer. Suppose, in fact, I think in 90s, Jones had come when I was a student to math science. Unfortunately, I had gone for some other conference, but then he apparently said that there is a 9 crossing knot, which is 942 in the Rolfson table. He said that that is a chiral knot, but none of the knot invariants can distinguish it. This is the statement he made, and I was a student, I was working on this. I said, since I have an ocean of results, I should be able to check. Okay. So, the simple thing I took was an SU2, I took a higher dimensional representation in the physics language angular momentum as spin 3 by 2, and I showed that 942 and 942 star have different polynomials. Okay. So, it was very exciting to me that Jones was saying this, I could get this, but there is more thing. This ocean also tells you that you can attempt classification, right, in the sense that I should be able to show that there is a 1-to-1 onto map between a set of knots and set of these invariants. They should be 1-to-1 and onto. That has not been achieved so far. Okay, at least there is a class of knots, at least I have not been able to achieve within Chern-Simon's field theory framework. There is a class of knots called mutation, and we are not able to distinguish them, and there are still problems. If I want to say that this is a not invariant and I tell you that this result gives you a not invariant, you are not happy. You want to see the way the Jones or Homefly or Kaufman has seen to write it in the polynomial form. So, can we write a polynomial form for any arbitrary knot with any arbitrary representation, arbitrary gauge group is still an open question. Okay. So, I hope the problem is clear to you. So, SU2, if I put the defining representation, fundamental representation, we will see that if you work out for some examples in the discussion session, you can see that you get back the Jones polynomial. So, now we have a physicist's way of understanding Jones polynomial are expectation values of Wilson loop operators, where the Wilson loop carries fundamental representation of SU2 gauge group. Okay. So, now I said that I can change the representation to higher dimensional representations. I can also change the group to other groups. So, the table can keep going on. Just to confine here, I will Homefly PT is the right notation. There are independently Pretsky and so those set of people have done it. So, it should be called Homefly PT. Homefly PT polynomial is when you take SUN defining representation, and if you see here by higher rank I mean higher dimensional representations. If you take higher dimensional representation other than fundamental, what you will end up getting is the colored Jones for SU2, and for SUN you will get colored Homefly PT. Okay. So, this evaluation, well, I am sure Ilya will be doing it. So, this polynomial is in a variable q, and you will ask what is that variable. If I see a quantum field theory, if you remember in my quantum field theory, I should have an action where these things I will put a coupling constant in front. So, that coupling constant will be here and n is the rank, the SUN has rank n. So, capital N is the rank and the variable q is not arbitrary, but a root of unity depends on k, which is also has to be an integer for gauge invariance of the field theory. So, this is the variable which will show up in SU2. SUN will have one more variable which is dependent on the rank, and we can write analogous to Jones, you will have a home fly which will be dependent on variable A and variable Q. Okay, you do not specify the capital N. There you specify capital N to be 2, then A becomes Q squared and everything will shrink to one variable Q. Okay. So, as I said, it is not just giving me formal expectation value as not invariant, but I can actually do the computation and get the polynomials. Only barrier in writing the polynomial form is that we will see that these invariants involve a quantity which is called as a quantum Wigner 6J symbols, and this is very non-trivial object. We do not know for any arbitrary group. SU2 we know completely, SUN we know some of them. So, this puts a barrier because the invariant involves them, this puts a barrier in getting the explicit polynomial in variable A and Q. Okay. So, that is the first barrier we face. Okay. How does the computation go? If you have an arbitrary knot, which I have tried to draw it as if it is a closure of a braid, you can slice it into two pieces. So, this is an arbitrary knot in S3 carrying a representation R, knot or a link, and I am putting the same representation. So, if I slice it, you do see that the boundary has 4 punctures and these two boundaries should be oppositely oriented, and then you can use the prescription that you can associate a state corresponding to this as psi, and similarly you can have basis evaluation for a 4 punctured. I need to write the state psi which I have written here in terms of a basis. If you see here, when I want to understand these two crossings, what I do is that I exchange these two punctures. I exchange it twice to get these two crossings. So, this is done by a monodromy braiding matrix, and this I can do if I could write the state psi in the eigenbasis of such an operator. Okay. So, this is what I do, I choose two bases, these are the two bases, equivalent bases, and I will use this basis depending upon whether I need to exchange middle to this basis if I want to do it in the side 2 and so on. Okay. Sorry, this is middle 2 and that is side 2. So, once you want to write the expectation value, since they are oppositely oriented, the states will be in the dual state for this psi and phi, and you just take an inner product and that should give you some real quantity, and that is what we call it as a not invariant. And to evaluate this, we are going to go into the basis which exchanges the punctures, and both are equivalent bases. You can either work with this basis or this basis for the braiding operator. Because there is a braiding relation, the trilinear relation bi plus 1 bi relation, you know that you cannot do a braiding in the first and second in the same basis and second and third in the same basis. If I want to do a braiding in the second and third, I have to move to this basis, but both are equivalent. So, there should be a similarity or a unitary matrix transformation relating these two bases, and this turns out that this matrix has all the properties like the quantum Wigner 6J symbol. Okay. So, they are the, suppose I confine to SUN group, these are nothing but the quantum group Raka coefficient, which is proportional to the quantum Wigner 6J of SUN. Okay. So, just a bit of, I am sure when Ilya is going to talk about quantum groups, probably he talks about these algebras. So, just like your SU2 algebras, you do see that there is a slight variation in this algebra which is dependent on a Q operator. So, if you see here, if you take Q tending to one limit, you will get Jz. Okay. So, this is what we call it as a Q quantum group. Q is actually that Jz is promoted to the square number of Jz, the meaning of it is this. Okay. In fact, there is lot of activities on Q calculus, Q integration, you know, it is it's a different kind of and it is all very beautiful, everything, you know, works out so nicely. So, it is like classical mechanics, you go to quantum mechanics, initially people were hesitant about counterintuitiveness. Similarly, any number you have, you replace it by a Q number. So, then many physics becomes the quantum group versions of the physics. Okay. And the basis which I was showing is basically that you can combine the first strand and the second strand, the combined one will have, the tensor product will have a combined state which I am calling it as J12, and then the third strand will give you this. Similarly, here you can combine second and third, then the first, combine them and get the J. Okay. Both are equivalent bases, as I said, and these two bases are related by the unitary matrix, which in the context of SU2 it is SU2 quantum Raka coefficient. Okay. So, this is for the 4 punctured boundary, one S2 boundary which you have when you slice the S3, but you can also slice the S3 in such a way that there are 3 S2 boundaries, there are 2 S2 boundaries, there are many S2 boundaries. And I would like to do it in a way that each S2 boundary has only 4 punctures. So, the question is that can every knot be obtained by gluing these pieces with braiding operation is a question mark. Okay. But at least there are some knots which I can use these as a building blocks, arbitrary braid word here, I can glue it here, I can use this to cap it. Finally, I can draw the knot by gluing these building blocks, at least some knots. Okay. And the braiding operation also, I said that if I am exchanging between the first and the second, it is B1, and if it is you are putting a orientation, then the orientation I am keeping track by putting a minus sign. So, the orientation is anti-parallel here, and you can also have parallel. You know, both the orientations can be in the same direction. You can have parallel right handed braiding, left handed braiding, inverse braiding. These two combination will give you an identity operator, and anti-parallel in the same way. And basically what you need is the eigenvalues. If I do the braiding operator parallel or anti-parallel, right handed or left handed, I need the eigenvalue because these are the eigenvectors of these operators. And these eigenvalues we take it from conformal field theory, which depends on quadratic Casimirs for representations. So, these are some numbers in variable q for you. Okay. So, suppose I give you a complicated knot like this, which is 10154. First I need to redraw in a fashion which I can put it in the building block. Okay. So, that is the first step we need to do. If we could achieve that, similarly I have given you a couple of knots, most of the knots I could bring it to that building block. Okay. So, if I can do that by putting, these are the links, that is why I have shown a different color, but if you can redraw any arbitrary knot into, like if you splice it here, you will get a 4 punctured boundary, and you can start using those building blocks. Sometimes you may be forced to put 3 or 4 S2 boundaries in the middle and you can draw them. Okay. Like I am just showing one specific knot. In fact, I got to know that it is called these ways of drawing where I put 3 boundaries, this kind of redrawing any knot if you can achieve, they are called arborescent knots. Okay. So, this was something which I have an Indo-Russian project. Apparently, the papers in Russian have this terminology. It is like some kind of a tree diagram. So, they coined the word arborescent, and they also shown that there are some knots which are not arborescent. Yeah, Conway, right? I see. Arborescent classification. I see. Classification in the sense the polynomials are different, just tabulation, like the Rolfson.
No, not the tabulation, classification.
No, classification into arborescent and non-arborescent.
Of arborescent. Which knots are arborescent?
Which knots are arborescent, but I am asking whether if there are 2 arborescent knots which share the same home fly, colored home fly PT, not in that language. Okay, fine. So, yeah. Yeah, no, it is before that also I got to know from Kaufman in one of the conference. He said Conway has already called it as a Conway method, and it was not known as arborescent at that time. Anyway, so now we follow this arborescent terminology, but it is apparently known, this tree diagram way of drawing, some knots could be drawn. 818 for example cannot be drawn this way. Okay. 818 cannot be drawn this way. So, in fact prior to 2012 I always thought every knot I should be able to somehow struggle and redraw it this way, and 818 we were not able to do, and then the Russians showed this paper, and then Kaufman also showed that Conway has this, and 818 does not belong to this class.
So
they are called non-arborescent knots.
So
yeah.
is there any something that detects that whether it is?
That is a very good question. So far I have not been able to see what can distinguish. Suppose I give you an invariant, can you say it is an arborescent? That I am not sure. So far we have not been able to figure it out. It is just that I can say
something so that
arborescent means I know how to do the computation using this method. Non-arborescent is much more a tedious computation, that is all I can say.
some
It becomes,
property has
yeah,
been
it helps me to simplify my computation, but as a polynomial whether there is a property between arborescent and non-arborescent is not obvious. Okay. So, as I said, whenever I want to write the invariant, I have these building blocks. For each of these building blocks I have those states, and the braid word will give me those eigenvalues. So, I can systematically write out in terms of the braiding eigenvalues. Sometimes it is parallel, sometimes anti-parallel and so on. So, and then you have to go from one basis to another. So, you have this duality matrix. So, it is a very systematic exercise to write down the invariant in terms of these Wigner 6j symbols and the braiding eigenvalues. Of course, braiding eigenvalues are known in variable q, but these Wigner 6j's are known by Kirillov-Reshtikin for SU2 quantum group, not for other groups. Okay. So, this is the result for the initial knot which I showed 154, and it is doable, like we took a higher dimensional representation like a symmetric and we could achieve this. How could we achieve this? We need the 6j symbol, as I said. SU2 Kirillov-Reshtikin has this formula. So, the closed form quantum 6j for SUN for arbitrary representation, just like here you had J1, J2, J3, J4 which are arbitrary representation of SU2, you know this nicely in an algebraic form. Okay. This is still an unknown question, still an open problem, it needs more minds to get in and see whether one could write In fact, if you go back and look at Kirillov-Reshtkin, there are these hypergeometric series, ways of looking at it, and he comes up with a neat algebraic expression. So, this is still an open problem. Okay. So, we have some identities of this quantum Wigner 6J by which some elements can be fixed, some representations can be fixed. Okay. So, these are data which we have, and we play around with this. Mainly is if once I have this matrix, I can work out the polynomial form, nothing more. Aim is to work out the polynomial form for as many knots as possible, and if a mathematician says this knot and the other knot has the same invariant, we think that we have an ocean of invariants, we should be able to distinguish if we know the 6J sum. Otherwise, we are stuck. Okay. So, this is the status in which we were working. One of the things which I wanted to say here is that twist knot is a this is the kind of twisting we look at. There are p full twist here, and these are called as Kp in the literature, where p is the number of full twists. For such a knot, this is also an Arboreson knot. We could write that invariant. We could write it in terms of the braiding eigenvalue. You see here there is a 2 crossing invariant and a 2p crossing invariant here, the braiding, and then there is a Wigner 6J taking you from the side strands to the middle strands. It is very simple. Polynomial form of this we knew only up to 2 boxes of SUN. We could write the Raka matrix only up to 2 boxes. We did not know how to write the polynomial in general, but then looking at Kauge, these people, we could generate and write this result for arbitrary symmetric representation. Okay. So, this is the theme of this talk today, that I just want you to show what made us work out this twist knot polynomial from a different picture. After we worked it out for different p's, we wrote these results and extracted these coefficients. You understand? So, this we worked it out by a different method, and from there we inferred these coefficients. Once we inferred these coefficients for different representations, then we attempted a formula like Kirillov-Reshtkin. So, this was one considered to be very important result, which I think people are using, because any arbitrary symmetric representation for Arboreson knot invariant, now they can compute. Number of crossings can be large, but now they can compute for any arbitrary symmetric representation using our closed form expression, which is similar to Kirillov-Reshtkin. Okay. So, let me just explain. The hard dot means it is a conjugate representation, and this is the symmetric representation and conjugate of the symmetric representation, and these kinds of Wigner 6J of SUN we have given a closed form expression. Okay. So, the closed form expression, this is our conjecture. The reason why we call it as a conjecture is because we have only validated it, we have not rigorously obtained them, but it seems to be working. Any arbitrary Arboreson knot, we work out the polynomial, it turns out to be a polynomial in variable a and q, at least for 4 boxes, 5 boxes and so on. So, in that sense we feel that it should be correct, but we found this from the root which I wanted to spend some time. So, only thing what I want to say here is that it is almost similar to your Kirillov-Reshtkin, but there is a slight n dependent factor here and there is a CZ. So, these are the slight modification which we had to do and rewrite it in terms of roots and weights. This is what we did, and we know we also looked at a couple of low dimensional representation and fixed these CZs. So, this is the work which we could do and get a closed form expression for the. So, once we have this, any Arboreson knot for symmetric can be worked out. Okay. Our conjectured form of SU and quantum 6J can be used to work out colored Homefly PT for many arborescent knots and links. This was possible only due to our twist knot polynomials using different method. So, let me explain how we went through to work out this twist knot invariance. So, this started with looking at the paper by Habiro. So, this is all mostly mathematicians work. So, it is where he writes it in terms of this Q-Pochamer kind of form for the trefoil, and this n is an arbitrary representation, higher dimensional representation, the subscript n, sometimes you can call this as a colored Jones. Jones is when you put fundamental, for n greater than 1 it is going to be called as colored Jones. So, he had this form, and then there was this extension from trefoil to look at arbitrary twist knots with positive p. So, as I have demarcated here, you see that there is negative p and a positive p. Positive p equal to 1 is trefoil, negative p equal to 1 is figure 8. So, it appears that if we have some handle on trefoil and figure 8, we should be able to generalize to both p less than 0 and p greater than 0. Okay. So, looking at this, Mossbaum, this was in 2000, this 2003 Mossbaum had tried to put in a twist factor. Okay. So, this is one modification which is and also these are the Q binomial coefficients which can be rewritten in this fashion. And this is the non-trivial part. When p is equal to 1, this twisting factor is not there. When p is not equal to 1, you start getting some kind of a twisting factor. Okay. Similarly, figure 8 also had this form with a different function, and then there is a twisting factor for p negative. Okay. These are the motivations which motivated us to look at colored Homefly. Okay. Whatever was done for colored Jones, it motivated us to look at colored Homefly. In fact, not even colored Homefly, we went beyond that, we went to the categorified, or they call it refined, which is what we call it as a super polynomial. Okay. So, there will be 3 variables q, a, and then there is a refinement parameter t. So, this was also available for trefoil. For arbitrary representation, they had it for trefoil, and then the Russian group had it for figure 8. So, our job was like, look at it like the earlier problem. If you are a student, Habiro has given this, let me try and do this, you know, for both figure 8 and trefoil, and similarly I would like to see whether these two results can be generalized for any twist knot. Okay. And then there were some more results for phi 2 and also 6 1. These corresponds to the p equal to plus or minus 2, but for only specific representation, n equal to 2 and n equal to 3. Okay. So, these were the motivating data which is available, and we wanted to guess a twisting factor. Okay. And this is completely nothing to do with Chern-Simons. Aim was to extract the Wigner 6J after we work out this. That was the reason why we went through this. Okay. So, then we saw a pattern, we tried to redraft how the super polynomial looks, and once we started seeing a pattern, we came up with rewriting as an Fn with some twisting factor and so on. Okay. So, this is what we did. The only thing is that there were 2 summations here, for p equal to 2, and then it appeared that for any p, you will have p summations. Okay. So, this is our conjecture. This is a conjecture for p positive and this is a conjecture for p negative. Okay. So, as you see here there is a multiple summation, and if you want to do volume conjecture and so on, it had to be with a minimal number of summations. We wanted it to reduce the number of summations. That was the only reason why we did this Bailey chain. This is, you can rigorously prove how to go from the multiple summation to a double summation. Okay. So, this is there in the paper. So, there is a series of steps from which you could get the super polynomial. Why I call it super polynomial is not just two variable, there is also a refinement variable or categorified variable, and this can be reduced using these Bailey chains into a double summation. Okay. So, we have for positive p and a negative p, we have these results. And in fact, this result was the one which we could take t to minus 1, then it will become colored home fly, and we have an expectation value of Wilson loop operator for these representations written in terms of quantum Wigner 6j, and we could fix those Wigner 6j's by rewriting this p from p 1 to 5 or something, we can extract out those coefficients. Okay. So, we did an inverse process because it appeared that it is very difficult. If you ask a quantum group person, he says it is very difficult to get, and we wanted that to write the polynomial, and this was a neat way of getting those Wigner 6j. Once we got the Wigner 6j, any Arborescent knot we could work it out for symmetric representations. Okay, not for, so this n refers to the symmetric colored representation. Okay, so to validate our conjecture on our twist knot invariance, we have various limits to take. As I said, you can check that the colored Jones polynomial matches if you take t equal to minus 1 and a equal to q squared, and t equal to minus 1 alone will give you colored home fly pt, and we have also worked out for many knots in one of our paper in 2011. Zodin Mavia was my former student, and yeah, so we have done cases and checked for n equal to 2 and 3, all these conjectures are matching with this formula. Other thing is that there was a linear skein relation. So, these were validating that our conjecture is right. Many cases which were there, we checked that they were all matching in various limits. Okay. So, this is just to, so and then we also have these are called the refined invariants, colored Kohanov is what we can call it. So, these were also validated. So, with this result, we wanted to look at figure 8, for example, is also a twist knot, and Keshev had this beautiful relation for the colored Jones. So, if you take colored Jones which is in one variable, and if you replace that variable as the nth root of unity, the same as the color, and take the log of it and take the limit, he gets beautifully the volume, and I am sure Abhijit will tell you how to find the volume for ideal tetrahedra of knot complements. So, in fact, this last month when I was in Santa Barbara for a knot homology conference workshop, extended workshop, I met Keshev. One side is a topological invariant, one side is something which captures the geometry. How did you even think of relating one to the other is what I was asking him. It is a very completely different thought process, you know. We can work out these polynomials, but why did you think it should be related? What he was saying is that whenever you write it in terms of q numbers, q pochomers, and if you do the asymptotics, q pochomers are like dilogarithms, and this dilogarithm has very close connections to volume. And he said some name, I forget, one of his senior prof said that since you have it in q pochomer which has dilogarithm, it might have connections to volume, and then he worked out for the figure 8, that is what he said, you know, and it matched. So, it is very beautiful to get some insight from the horse's mouth, so I thought I will share with you. Okay. So, this is the statement which I think Hitoshi is here, and he has also done for, I think, Borromean and other examples. You have verified this for more examples or lot of examples. The volume conjecture?
Phi 2.
Huh? Phi 2? Okay. Yeah. So, I am feeling very nice to give it here when I can meet people who are the main authors of this work. Okay. So, I just want to give a flavor of classical A polynomial. So, this, I do not know whether this is the right terminology to use here. They are like, if I look at it as SL2C Chern-Simons, and I can start looking at it from the SL2C Chern-Simons point of view, but this is also called as a character variety of the fundamental group of the knot complement. So, what is knot complement? You take the knot, you thicken the knot, and that is what will give you the, you remove it out and whatever remains is the knot complement. It will have a toral boundary. Now, you can study fundamental groups of these knot. There is a Wirtinger's presentation where you can start calling this P's as A, B, C and D, and you can write at every crossing, oops, at every crossing you can follow a closed loop or follow some convention and write identities, and after you do this you can eliminate some variables, and in fact here in this case you will have only 2 variables, and we can write a constraint equation it should satisfy. So, this is the fundamental group, and longitude of course you can rewrite it. So, I have called it as A, B, C, D. You can write the longitude and eliminate it by using these properties, and write the longitude also in terms of A and B. Okay. And then you can have a representation from fundamental groups to SL2C. So, you will have for the A, which is this, B, and then you can use this constraint, and this constraint will give you the value for D. Okay. So, this D, do not confuse this D with the D which I put in the diagram. So, this value we can substitute and then determine what is rho of L, and as I said, rho of L, L is this, since I know A, B, the rho of A and rho of B from here, because I am going to substitute the D, I can write what is rho of L. Okay. So, essentially you see that there will be an x and a y, and you have to write a polynomial in variable x and y. Okay. So, you try to put this L in terms of A and B, and rho of L is this, and then you can find a relation between y and x. So, this is what is done here. This relation is like a y as a function of x, or you can say that it is the 0 locus of the A polynomial. Okay. If you want to write a circle as x squared plus y squared equal to 1, you can write y squared as square root of x squared minus 1, or you can call the circle equation as x squared plus y squared minus 1. So, that is the A polynomial and this will be the 0 locus of your A polynomial. Okay. How do we see it from the Chern-Simons theorem? How do we reproduce this result which I tried to systematically say from Wirthinger representation, putting the longitude, working out the matrix, getting this equation. Can we get this equation from the Chern-Simons approach and which has lot of resemblance to Keshev, Murakami work. Okay. So, the way it is done here is that you look at SL2C Chern-Simons. The claim is that I should be able to write the colored zones, I am confining to SL2C. So, I will look at the SU2 invariant of a knot. So, this is the colored zones polynomial where I will replace the q variable as e to the h cross tends to 0 and the color is infinity. You try to rewrite it as an exponential, actually you could have taken a log, I have just taken it on the other side and written it as an exponential and there is a series expansion. So, this is like a perturbative expansion of the SL2C, you can say partition function, exponential is like the partition function, you have a perturbative. So, this will be like the first term will be like classical and then you will have corrections, quantum corrections and so on. So, the leading term, the real leading term should be consistent with Kashev's conjecture. So, the real leading term is volume. The subleading term besides this complex coefficient can be recast in this fashion. Okay. So, what is x? X is nothing but you replace this as q to the n as x, h cross tends to 0, n tends to infinity, but x remains finite, that is the limit in which we are working. So, you will have a variable x showing up from here. So, the variable y should be such that this should give me the 0 locus of the A polynomial. So, let me give you an example. Okay, so, conversely you can rewrite this as log, then you will have a 1 over h cross s naught of x. So, you can say log y is minus x d by dx of log of this with this condition. This additional condition we did not have in the earlier case and you had a mod. Now the mod is modified. Yeah.
So, just go to the earlier slide.
Yeah.
So, you have an integral which vanishes on some curve. How would you get the curve?
Yeah, I am getting it. I am just doing it because we know the left hand side and then we deduce this. I am just coming to it. So, what I am saying is that here I do not know, but what we are saying is this is a generalized volume conjecture which goes beyond the volume conjecture and it has to give you the character variety and we want to find out whether we will get the same for the figure 8 like this. This is what I am motivating. Yeah. So, I am saying that the left hand side which I have written now on the right hand side with the log where the exponential is removed, okay, and then I am doing the minus x d by dx. This thing is calculable and then I should be able to write y as a function of x. Or equivalently I can say it is like the 0 locus of the A polynomial for the specific knot k. Okay. So, in fact, this can be done for any knot. In your case when we did the volume conjecture, volume is non-zero only for hyperbolic knots. Hyperbolic, the knot complement should have a hyperbolic geometry, but this one can be done for even the torus knots whose volume is 0. And these are another set of polynomial invariants which are called the A polynomials, classical A polynomials. Okay. Okay, so I will just explain this also and then I will come to a specific thing. So, the same thing we could do it for the super polynomial which is dependent on 3 variables, and the corresponding thing we will call it as a classical super A polynomial. Okay. And the similar expression can be written for the leading terms besides the volume term, and you can call this as a super polynomial is one where this is going to be the 0 locus. How do we do the computation? So, we have these invariants. So, at least for the twist knots we have a very closed form expression. This is the most general one, you can put t equal to -1 and work with a equal to q squared, you will get your colored zones. So, if I work this out, I know the whole ladder, right. If I know this, then t equal to -1 will give me the a polynomial which is derivable from colored home fly. If I put a equal to q squared, I will get the a polynomial associated with colored zones. So, this is the most general one, and as I indicated that because they are in q Pochamer, I can write it in dilogarithm in the large scale limit, and then try to rewrite this as we call this as a perturbative way of writing it in the h cross tending to 0 limit. And this w tilde, if you replace all these q Pochamers in this fashion, you can rewrite it involving the dilogarithms in the limit, large scale limit you can write it. So, this working it out, extremizing it like a semi classical approximation. So, we do this set of algebra and then we end up getting y in this fashion. It is just taking the limit, rewriting w tilde and extremizing it, and we find out what is y. Okay. So, this is what is done, is just algebraic computation, and then we end up getting a polynomial. In fact, it is a super a polynomial, and then you can check.
You have a closed form?
Yeah.
You have a closed form for a polynomial of twist knots.
For phi 2, some knots we have worked out. It is very laborious, but in principle case by case can be done. In fact, Zinju San was actually helping us with the writing a neat program to get this result. Okay, so there is also a quantum version of it which was developed by Stavros and later on Gukov, that there exists an operator which is like an eigenvalue equation. This is like a ladder operation, it takes the color n to color n plus 1, and then you write a quantum version of that operator. Now, you will have a q variable, q is e to the h cross, if you put h cross tends to 0, q is 1. So, then all your results were independent of q earlier, classical. Now, quantum will depend on the q variable. Okay. So, the neat thing what is very inspiring from his work is that it could be rewritten using these two relations. You can write some kind of a skein relation between different colors for the same knot. Skein relation usually was one crossing more, one crossing less, but this is like a skein relation for the same knot with the color n plus k to n, and each of these coefficients are going to be functions of x and q, and this you can replace it by, suppose I want to write j n plus k, I can say it is y to the power of k on j n, right. So, I can write y to the power of k for here, I can just keep it as j n, in between terms will be y to the power of the appropriate power and multiply the whole thing by j n. That is nothing but your operator which is a function of x operator, y operator and q variable. So, this is what is the quantum a polynomial. This is also doable within the knot theory for many knots, and if you want to get your classical a polynomial which has physics interpretation from SL2C or from Wirtinger representation of finding the 0 locus by looking at character variety, they can all be derivable by taking q equal to 1. Okay. So, I think I put it here in a neat block that these are super polynomial. You can get a equal to q squared alone if you put, then you will get the refined polynomial. If you take t2 minus 1, okay, so this is not working. So, if you take t2 minus 1, then t2 minus 1, then this is we call it as the lambda deformed or q deformed, and a equal to q squared, you get your quantum a polynomial, and here they are the classical analog. By classical analog I mean q equal to 1. So, this goes to the classical a polynomial, this goes to the classical super a polynomial, and all the other things fall.
So, the conjecture is that the lower row is equal when q equal to 1, that is the conjecture.
It is a conjecture.
Is the above also conjecture?
We have at least verified, we have verified for the phi 2.
No, but the question
This
is
one.
that that's also conjecture.
We can treat it to be a conjecture, because in the sense that we have only validation, we do not have a proof that this should work for any knot.
The lower conjecture,
This one,
that's the AJ conjecture.
that is the AJ
That has
conjecture.
been proved for twist knots.
That has been proved for twist knots. So, I do not
Yeah.
think we have proved it for twist knots
No,
for this case.
Yeah, I don't know about the top one. The lower row is
Yeah.
Tang has proved it. Tang proved it.
Okay,
for
okay,
twist knots.
okay. This one? This one is done for the twist knots.
For
Huh?
twist knots.
So, maybe we should attempt and see, but the calculation itself is so horrendous. I do not know whether we can do for any p.
He doesn't calculate the polynomials. He goes through a different thing.
Okay, maybe I should see the.
Kaufman bracket skein module.
I see. Maybe I should see the proof, but I don't know whether the proof is extendable to
I
colored
don't
home fly. I need to see that. Okay. Okay, so as I said, that super quantum a polynomial is such a huge expression, and then getting q equal to 1, we got the classical a polynomial, and I hope I have given you some flavor of what is happening in the physics way of looking at the mathematician's problems, and I hope, yeah, I am open to questions. Yeah.
So, do you are you able to from this get the volume conjecture? Because if you have verified the row below, do you assume the volume conjecture and then get the?
That is right. That is another way of saying, or I just go on the tower on both sides, because in the classical I know that this tower is right.
Assuming the volume conjecture.
Assuming the volume conjecture, and then once I have this, I can also verify for the phi 2 that the classical a polynomial matches with the quantum super a polynomial. In fact, at the super a polynomial level we are there. Yeah, but we are assuming the bottom one is.
Are there more questions? Okay, then maybe we should thank the speaker,
Okay.
and we have something from the mathematics department.
Oh, I see.
Because you'll be leaving, this is
Okay. Thank you.
So,
Thank you.
so-